Today what we're going to look at is the reason why some salts can affect the pH of a solution. And the ability of a salt to affect the pH solution comes down to their Bronsted-Lowry properties. Okay, and we know that in a Bronsted-Lowry theory, water is amphoteric, can be both a proton donor and proton acceptor. And so that means that when mixed with different ions, it could either donate a proton to that ion or accept it. Okay. So my water in this case is both a proton donor and proton acceptor. So in this case, when it's reacting with an acid, it acts as a proton acceptor. In this case, when it reacts with a base, it acts as a proton donor. Well, when I have cations and anions in water, they can react with the water molecules in a Bronsted-Lowry reaction to produce either protons or hydroxides. And so we say if this reaction occurs, we call it a hydrolysis reaction. So we can use this knowledge now to look at why salts affect the pH and then start to predict which ones will affect the pH of a solution. Okay, so let's look at first a salt that contains cations from strong bases and anions from strong acids. So our first step would be to identify what our strong acids are, and we remember the 6 from last year, and the ions that they produce. So we're looking for salts that have these anions. And then we can identify our strong bases. And we know that they're group 1 and group 2 hydroxides, and we have 2 examples here, and identify their cations. So therefore we're looking for salts with these cations and these anions. So for example, these salts. So if we were to take these salts and we have a solution of them, and I was able to add some universal indicator, which would indicate the pH of the solution, I find that it has a green color. So I've added universal indicator to any one of these solutions that has a green color. This green color tells me that pH is neutral. So what this tells me is that these salts do not affect the pH of the solution. So the question is why? Well, salts derived from strong acids and strong bases give a neutral solution because neither the cation or anion can react with water appreciably. So neither the cation of a strong base or the anion of a strong acid cause a hydrolysis reaction. The reason, my cations do not have a proton to donate, so therefore they can't act as a Bronsted-Lowry acid. My anions, because they're from a strong acid, they're too weak of a conjugate base, so they will not accept a proton from water. So they won't cause a hydrolysis reaction either. So let's look at our next example, where we have cations from a strong base, but anions from a weak acid. So here are some examples of weak acids. We know that weak acids are all acids that are not in our strong list. And the anions that they would produce, as an example, our cations of our strong bases are group 1 and group 2 hydroxides. So they're cations. So therefore we're looking in this case for salts that contain cations from group 1 and group 2 and any anions that are not from my strong acids. So we have a few examples here. Again, we'll take their solutions, we'll add our universal indicator to them, and we get like a purple color. So if we look at our universal indicator, that means that we're here. That means that these give a solution with a pH greater than 7. So when we look at these, we know that they produce a basic solution. Okay? So my cation plus my anion. I'm using B for the symbol for my cation. Okay? Cations from strong bases, we already know, right here, it does not have a proton to donate, so it will not cause a hydrolysis reaction. Whereas my anion can accept a proton because it's a strong enough conjugate base. So how does this look? So let's look at a specific example. Okay? When we're looking at specific examples, first we have to write out our dissociation equation for our salt so that we know what our 2 ions are. And after we have that, we know that my barium ion is a group 2 metal. Since it doesn't have a proton to donate, it will not affect the hydrolysis of the reaction. Incidentally, it will not accept a proton either because it's already a positive charge. Whereas my cyanide ion is an anion of a weak acid. So therefore it can act as a proton acceptor. Okay? It's a conjugate base to my weak acid. And when it accepts a proton, it's going to form that weak acid. In the process, it produces our hydroxide ion. And so therefore we get a basic solution. When explaining the effects of salts on a pH of solution, if it causes a hydrolysis reaction, make sure that you write it. And what about salts that contain the cations of weak bases but anions of strong acids? Again, we'll identify our strong acids and our anions, which we know. But in this case, our weak bases are going to be our molecular bases. And the examples that we're going to use are ones with nitrogen in them, or derivatives of ammonia. So we have here ammonia, or methanamine, or N2H4. So when they accept a proton, they form these cations. So therefore, we're looking for a salt that has these cations and one of these anions. Okay. So here are examples of some salts. So if I have solutions of them, we're going to add our universal indicator again to it, and we get a beigeish, orangish color. So if we look down here, we have a lower pH. So as a result, that tells me that my pH is less than 7. And these salts will produce an acidic solution. Okay, so when a salt that has an anion of a strong acid and a cation of a weak base are dissolved in water, we get an acidic solution. Okay? The reason being, my cation of my weak base can act as a proton donor. It has a proton to donate. And so it will react. Whereas my anion is too weak of a conjugate base to accept a proton, so it will not react and cause a hydrolysis reaction. So for example, ammonium chloride. Again, we'll write our dissociation equation. Okay? We know that our chloride, because it's an anion of a strong acid, is too weak of a conjugate base to accept a proton from water, and so will not cause a hydrolysis reaction. And this ion will not affect the pH of my solution. Whereas my ammonium ion has a proton to donate, and so therefore it will cause a hydrolysis reaction, producing my hydronium ion. And so as a result, this causes my pH to go down. Okay, what about if I have a salt that has both cations of weak bases and anions of weak acids? Again, we'll identify our weak acids and their ions. We'll identify our weak bases and their cations. Come up with some example salts. Now we're going to test these, so we'll get a solution of them. And when we add universal indicator to them, we get a range. So some of these salts are going to produce an acidic solution, some are going to produce a basic solution, and some are going to produce a neutral solution. So now the question is why? Because they can give us either an acidic, basic, or neutral solution, we need to have a reason to explain this. Well, we already know that cations of weak bases can act as proton donors and will form hydronium ions. And anions of weak acids will do the same, and they'll produce hydroxide ions. So now the question is, what's going on? So let's take a look at our example, ammonium cyanide. We know that when this dissociates, we're going to get our ammonium ion, and our ammonium ion is going to cause a hydrolysis reaction to produce our hydronium ion. And when our cyanide dissociates, it's going to cause a hydrolysis reaction to produce hydroxide. Now, since I have both hydronium and hydroxide being produced, they're going to react with each other. But they're not going to be produced at the same rate. One of them is going to be produced more than the other. Okay? And so the way that we can look at it is if we have more of this produced, then it'll be acidic. If I have more of this produced, it'll be basic. And if they're produced in equal amounts, it'll be neutral. Well, the way that I can determine which one's going to be produced more is if I look at the ionization constant, or the Ka for this reaction, and the Kb for that reaction. And if the Ka is greater, that means that I'm going to produce more of this, because this reaction will shift further to the right than this reaction. If the Kb is bigger, that means I'm going to produce more of this, and this reaction will shift more to the right than that reaction. Okay? So what I need to do is I need to be able to get the Ka for this reaction and the Kb for this reaction. But we're not given Kas and Kbs for conjugate acids or conjugate bases. What we're given is our Kbs for our weak acids and our Kas for our Kbs for our weak bases and our Kas for our weak acids. But we know this relationship. So therefore, I could calculate my Ka for my ammonium ion. And likewise, I have a similar reaction. I can look up my Ka value for my weak acid, and that would allow me to calculate the Kb for its conjugate base. So now I can see my Ka and my Kb. I can see which one's greater. So since my Kb is greater than my Ka, that means that this reaction is going to shift more to the right than that reaction. And since this reaction shifts more to the right than that reaction, I'm going to produce more of this than that. And so as a result, I'm going to have OH left over, and I'll have a basic solution. Okay, what about salts that contain highly charged cations? So, for example, aluminum ion. Okay? These salts cause a hydrolysis reaction, but it's indirect. What they do is when they're hydrated with water, so they're surrounded by their water molecules when they dissolve, right? Then what happens is that one of the water molecules that's surrounding them will then undergo a hydrolysis reaction. Okay, so for example, we take aluminum. When aluminum chloride or aluminum nitrate or any soluble aluminum compound dissolves in water, I'm going to have aluminum ions floating around. And those aluminum ions are surrounded by water molecules. Okay? And generally the amount of water molecules that surrounds an ion is double its charge. And so as a result, they'll form a complex ion where these water molecules would have the slightly negative end pointing towards the positive charge, and they'll form like a complex ion. And since we have a full ion attracting the partial charge, these water molecules will stay attracted to that aluminum, and they'll stay close to it. And that's why we have this. Now what will happen is, because of its structure, one of these water molecules that's surrounding it will ionize. And so now I have only 5 waters instead of 6, but I also have an OH. And I released one of my protons. Okay, so metal ions that do this would be like aluminum ion, iron 3 ion, copper 2 ion. Okay, and whenever they do this, it's usually double the charge.